Okay, so all right, so in this example, we're gonna go a little bit deeper, more like a computational kind of problems. Now, how many of you actually put things in your shopping cart but never check out? I do. Sure, some people do too. Suppose there's an online shopper for a particular website that start filling the shopping cart. 25% actually make a purchase, meaning complete the transaction. We have a random sample of 10 such online shoppers. So X is your random variable, is a person. It's a person that actually make a purchase, right? And the probability of that person gonna make a online purchase is 25%. So first, before we actually dive into a question, we need to answer the question: is this problem follow a binomial distribution? So let's see. Do we have fixed number of trial? Yes, we do, right? N equal 10. Right here. Yes. So here I got N equal 10. And what 25% in such a random sample of 10 actually make a purchase. So 25%, that's my P, my probability of success. P equal 0.25, right? That's my probability of success. So okay, two down, two more to go. Remember, we need fifth, right? 4. Is there are two outcomes? Is there a two outcome? Yes, right? Either you make a purchase or you don't. Right. Is the probability of someone making a purchase is independent to the next person? Yes, right? Yes. So yes, the problem followed by a binomial distribution. Now I want to know what is the probability that all 10 shoppers will actually make a purchase. So this means I want to know the probability of the first person making a purchase. Instead of writing purchase, I'm just gonna write P, okay, little p. And the second person making purchase, and the third person making purchase, all the way to what? All the way to the 10 person making the purchase. Right. So how many are there? So the probability of the first person making a purchase is 0.25, right? And the second one is also 0.25. And the third one also 0.25, all the way to what? 10% is also 0.25. And because we say they are independent from one another, remember, if you're independent, we multiply, right? Multiply. So 2.5 times 2.5 times 2.5, 10 times. 10 times. That is the same thing as what? It's the same thing as 0.25 to the 10 power. Okay? And if you plug in your calculator, it will be 0.0000, 1, 2, 3, 4, 5, 6, I think 6095. So the probability is pretty slim, right? It's the probability of all 10 people making an online purchase, all 10 random of a random sample is probably rare, right? So it makes sense. Right? It makes sense. Probably of all 10 people making such purchase is kind of rare. What about the probability of none of the shopper will make a purchase? So this means probability of the first not making a purchase. I'm just gonna say NP, not making a purchase. And the second person also not making a purchase. And the third person also not making a purchase, all the way to the 10 person not making a purchase. Well, the probability of someone making a purchase in a random sample of 10 people is 25%. So not making a purchase will be what? 1 minus 25% is 75%, right? So 0.75. So 0.75. Well, the probability of the first person not making a purchase is 0.75. And then the second one is still the same, right? Remember, it's independent and it's binomial distribution. The probability of success should be the same all the way. So the probability of the second person not making a purchase is also 0.75. And third one also 0.75, all the way to 10 person. So it's the same thing here. You multiply 0.75 10 times. So that means 0.75 to 10 power. And then you can work it out. What is that? Is what the 0.75? Maybe I'll do. Let's see, 0.75 to the 10 power. Is 0.0563. Yeah, but I'm just gonna choose 4 decimal places. So it's a little bit less rare, right? Is the probability of all 10 people not making a purchase is roughly 5.6%, right? 6%. All right. Now I don't know. I want to know. This one is a pretty important. We'll find out why it's important. I want to know if it just one shopper making a purchase. So how many possibility that remember we have 10 people here, right? We have 10 people in our random sample. So how many possibility that one shopper will make a purchase? So I'm gonna line them up. All 10 people will line them up, right? So I say the first person making a purchase, and then the last 9 won't. So the next person not making a purchase, then the third one not making a purchase, the fourth one not making a purchase, all the way to the 10th one. So the first one make a purchase, but the last 9 won't. So what is the probability here? The first one making a purchase is what, 0.25, right? Remember, they are independent events because we show that they are binomial distribution, so they are independent events. So the first person making a purchase is 0.25, and then the last 9 of them is not making a purchase. Well, not making a purchase is 0.75, right? We'll talk about it, 0.75. And then there's 9 of them, so to the 9 power, because 0.75 times 0.75 times 0.75, 9 times, right? And if you multiply it together, I got 0.01877. If I make a mistake, let me know, okay? Sometimes I do. All right, now what is another way that I can have one person making a purchase out of 10? Well, again, I'm line them up. Well, I can have the first person not making a purchase, but what if about the second person makes the purchase, but then the third one not making a purchase, the fourth one not, all the way to 10. So what do you think? Well, it's still 0.25 times 0.75 to the 9 power, right? Because you have one people making a purchase, which is 0.25, and then the other 9 won't. So still 0.75 to the 9. So the probability is still 0.0. I don't want to write 0 in the front. So it's still the same, right? 0.01877. Or what? Or I can have the first person not making a purchase, the second person not making a purchase, but the third person making a purchase, right? And the fourth person not making a purchase, and the rest not making a purchase. And again, I still have the same, right? To one person making a purchase, which is 0.25, and then the rest is not, which is 9 of them, which is a different order, right? But still 9 of them not making a purchase. So the probability is still the same. All the way through, all the way to what? All the way to the first 9 not making a purchase. The last person making a purchase. Right. And then you still have the same thing, 0.25 times 0.75 to the 9. And then you still have the same result. So because we're doing OR here, just one shopper making a purchase, but 10 possibility can happen because we do an OR here, because OR we use what? And we use multiplication because independent, or we use additional, right? Or is mean addition. So we add them up, we add them all up. If I would have add this all up, remember this is 10, 10 possibility, right? 10 possibility. So you add all of them, 0.01877 plus 0.01877, or just take 0.01877 times 10s, right? So it would be equal to what? 0.1877. Adding 10 times the same thing is multiplied by 10, right? Now, What if I want to know 2 shoppers will make a purchase? You're going to start all over the same process again. So the first 2 make a purchase and the rest of the 8 doesn't. And you have different possible combination, right? I don't want to do that. I don't know about you, but I definitely don't want to do that again. Right? What about the three shoppers, 4 shoppers? How many possibilities you can have, right? That's a lot of counting. Instead of doing that, there's a formula for us, which is very nice. If X has a binomial distribution with an n trials or sample size n and success probability P, that is X is a binomial distribution, have a parameter n comma P, right? For n is sample size, P is a probability of success. Then the probability of exactly X successes, remember exactly X, he highlights here, probably exactly X successes in the n trials is found by P of big X equal little x. I should have put a K there for the little x, but I'm just gonna use little x. P of x equal little x equal n choose x. So this part right here, maybe I'll write in blue. I'm gonna come back to that part later, okay? The part that we've been doing, so maybe in blue, maybe I'll highlight in blue. Right there, we'll come back. Now the part that we've been doing is this part. Probability of success, right? Remember, probably in the last problem, probability of someone is making a purchase is what? 0.25, right? 0.25. And we raise to the what power? Say only one person making a purchase, we raise to the first power. And then 1 minus 0.25 is what? 0.75. And n minus x, well, n is 10, x is 1, right? 1 people making a purchase, so 9. So that's what that part we've been doing right there. Now the blue part is called n choose x. That's combination. N choose x. It does not mean n divided by x. Okay, n choose x. This part right here is called n choose x. I'll show you how to do it in your calculator later, or maybe some of you already know how. So n choose x, the formula of n choose x is equal to n factorial. That little exclamation is factorial. In mathematics, is factorial. N factorial divided by x factorial times n minus x factorial. Now let me remind you, factorial. Factorial is what? If I have 10 factorial, 10 factorial is just 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Basically just 1 unit less than the before, right? To multiply backward. Same thing with like 20 factorial. So start out 20 times 18 times 17. Sorry, 20 times 19 times 18 times 17, etc. all the way to 1, right? So that's factorial. Okay. Okay, so let's see, let's check if we have the same answer as the problem here that we count. We kind of all like do the counting work instead of using the formula, right? So here the result is what? The result of just one shopper will make a purchase is 0.1877. It's roughly 19%, right? Let's see if we use the formula. If I were to plug in the formula, 10 choose 1. X is 1. Remember, X is 1. So 10 choose 1. Maybe I'll use green here. 10 choose 1. And then probability probability of success is 0.25. Raised to X was raised to 1. 0.75. 1 minus P, which is 0.75. Raised to the n minus X, which is 10 minus 1 is 9. 10 choose 1. Well, let's do the 10 choose 1 part first. 10 choose 1 is equal to, remember, n factorial. So 10 factorial divided by x factorial, which is 1. And then 10 minus x, 10 minus 1 factorial outside. 10 minus 1 is what? Is 9, right? So I have 10 factorial on the top. 1 factorial is just 1, right? Just 1 to 1. Times 9 factorial. Now the 10 factorial I can write it at 10 times 9 times 8, but I'm not going to do that. I'm going to say 10 times 9 factorial. Yeah. Instead of writing all out, 9, 8, 7, 6, etc., I'm just going to stop at 9 factorial. Right? Divided by 9 factorial, that's cancel out. So it's equal to what? 10. Right? The 10 ways that one shopper, we're going to make a purchase. There's 10 ways. So back up here, 10 times 0.25. What is 0.75 to the 9 power? 0.75 to the 9 power, which is 0.0751. I'm just gonna 08, so I'm gonna round it up to 1. So you take that, you multiply by 0.25 times 10. I got 1.1877. Exactly what we have up here. Right, what we have up here. By just using the formula, right? You can do 10 choose 2, right? What is the probability of just 2 shopper making a purchase? Okay. Now so before we actually do more of these kind of problem, I'm gonna show you how to practice doing the n choose x part. Okay, so suppose you have n friends. Say you have 10 friends. Here's 10 friends. How many ways you could invite x friend to dinners? Right. Now for the probability for doing the n choose r thing or n choose x here, we can use a calculator. So first you're gonna go to the math menu. It's kind of difficult for me to show. Maybe I can show here. Maybe I can right here. Let me clear all this. All right, the math button is right here. That's the math button. And then next, once you have math, you're going to go to probability. All right, so let me delete this. So I'm going to click math right there. Go over probability, PRB, using your arrow to the right. And see number 3 there, you have n choose r, right? But before we do this, I'm going to go back, clear, go back. So I want to do 10 choose 1. So I'm going to put 10 first. Put number 10 first and then go to math. And then go over PRB. And then go to number 3. You can click number 3, you can go down. I'm going to click number 3. So right there. Oh. You know, mine is a little bit different. So I'm going to clear CNC. You should go math. Maybe I don't have to do that. Some calculator, I have to do the 10 first, like my calculator. So 10, oopsie, keep making a mistake. 10, choose 1, it should be 10. Right there, right? Okay, so let me go back here. Now, the one at the ends are easy to do without even using the calculator, because think about it. Say, what is the probability that you can invite nobody to the dinner? Well, you have 10 friends. You don't want to invite nobody. There's only one way to do it. Don't invite nobody, right? So one way. There's only one way to invite nobody to your dinner, right? Don't invite them. What is probability that you can invite all 10 of them to your dinner? Again, one way, right? Invite all of them. Or you can, if you want to check, you can use the formula. Okay. What is our probability that you can invite one person to your dinner? How many ways you can invite one person to your dinner? Well, same thing, right? You can invite the first one, or you can invite the second one, or the third one. So they are 10 way. Yeah, 10 way. What is the probability? Let's go to the number 5. What is the probability that you can invite 9 of them to your dinner? It's kind of like the same in not inviting one to your dinner, right? So again, you have 10 way. But for the one in the middle, like 10 choose 2, 10 choose 2, 10 choose 3, 10 choose 4, a bit more, it's harder to do in your head or by reasoning, right? This one you actually have to use a formula, right? Again, I can show you here. Remember the formula for the factorial. Let me go back up here. N factorial divided by x factorial times n minus x factorial. I'm going to write down here. N factorial. So this is n choose x equal x factorial n times x. I'm sorry, n minus x factorial. So apply this formula, 10 factorial. I'm going to show you both ways, using factorial or using calculator. On the exam, you can use calculator. You don't have to show me all the math. 10 factorial. Oh, I don't need this one. No, I'm not doing this one. I'm doing the 10 to 2. So 10 factorial divided by x is 2. So 2 factorial. 10 minus x. 10 minus 2 is 8 factorial. I don't even need the parenthesis there. Okay, so 10 factorial on 10 factorial, I can rewrite it as what? 10 times 9 times 8 times 7 times 6. I'm going to stop at 8. I'm going to do just factorial. Okay, why? Because I can cancel with the 1 in the bottom. Right, and then 2 factorial is just 2 times 1, which is 2, right? So 10 times 9 is 90. 2 times 1 is 2, so 45. There are 45 ways to invite 2 out of 10 friends to your dinner. Right? So that's how we count. Or you can use a calculator, right? 10 choose choose. 10 choose choose. Again, math probability. Number 3. On the exam, you don't have to show me all these work here. Just 10 choose choose, give me 45, right? Use your calculator. Okay. Now, finding binomial probability. Okay, so go back to the online shopper things. Recall we have a random sample of 10 online shoppers from a large population, and the probability of success is 25%. So 25% is actually population proportion who actually make the purchase, right? What is the proportion? What is the appropriate distribution x be the number of online shopper in the random sample that's actually make a purchase? They're asking about distribution. Well, we know that it's the binomial distribution, right? But I never told you how to write the binomial distribution. Remember I show you, don't write this down. Remember I show you how to write the uniform distribution, U, A comma B, right? You can replace what is A and what is B. And then normal distribution, what is that? Normal distribution is what? Mu comma sigma. And what is mu, what is sigma? You depend on the problem, right? For the binomial distribution is bin, so binomial, n comma p. N is your sample size, which is 10 here. Oh, I should say bin instead of b. Bin, so n is sample size, which is 10 here, and the probability of success is 25%, so 0.25. That's what they're asking. The appropriate distribution for x, for the random variable x. So on the exam, if I ask you something like that, which I will, what is the appropriate distribution for the problem? If it's binomial distribution, then that's what you're going to say. Okay. What is the probability of selecting exactly 2 shoppers who actually make a purchase? Exactly 2 shoppers. Let me go. Did I? Okay, yeah, probably exactly 2 shoppers. Exactly 2. How would you write it? Exactly 2 shoppers. So this implies P of x equal 2. Right, exactly 2. Remember, go back up here. I want to know it's just 1 shopper. This is the same thing as say exactly 1. Right? It's the same way of saying exactly 1, P of X equal 1. Well, P of X equal 1, what is the math there? The math there is 10 choose 1, and then P to the X, which is P to 0.25 to the first, times 0.75 to the N minus X, which is 10 minus 1, which is 9, right? So here, P of exactly 2, so it's just 10 to choose. 10 to choose. P to the X is 2, so 0.25 to the 2. 1 minus P is 0.75. 10 minus 2 is 8. N minus X, 10 minus 2. Well, 10 to choose up here, we did the up here. We're going to put in your calculator again, which is 45, right? There's 45 ways to choose. There's our 2 out of 10 are going to make a purchase. So 45 times what? 0.25 to the second power. 25 squared. 0.0625. And then 0.75 to the 8 power. I got 0.1001. All right, all that multiply. So multiply all of them together. 0.0625 times 45. My final answer is 0.2816. Roughly 28%. Roughly 20. There's a 28% chance that 2 out of the 10 shoppers are going to make a purchase. What is the probability of selecting at least one shopper who actually make a purchase? At least one. So again, let me draw it out. Remember what we talk about binomial distribution is the count. It's the count distribution, right? It's count. So I'm gonna represent each of those each of those probability making a purchase in stick. So from 0 to 10, always start at 0. 0 people making purchase, 1 people making purchase, 2 making purchase, 3, 4, 5, 6, 7, 8, 9, 10. Wow, look at that. Perfect. At least one. What does it mean? At least one. At least one is mean I want to know the probability of X is greater or equal to 1. Right? On the stick, where is X is greater or equal to 1? Right here. Right? From 1, 2, 3, 4, 5, all the way to 10. Right? Except for 0. Now what you can do is you can do P of X equal 1 plus P of X equal 2 plus all P of X equal 3 all the way to P of X equal 9 plus P of X equal 10. I don't want to do that. What can I do is I can use the complement rule, right? What is the total probability? Add them all up. 1, right? 1. I want to know the probability from 1 to 10. All I have to do is take 1, subtract the 0, right? It's count, so I can do that. So we can use complement rule. Use complement rule. So P of X greater equal to 1 is the same thing of what? 1 minus P of X equals 0. I just subtract that guy out and you got the rest. Okay. So it's equal to 1 subtract. What is probability of P of X equals 0? Well, we use the formula. Remember P of X, big X equal little x. So here P of X equals 0. Just plug it in, right? And choose 0. Well, n here is what, 10, right? 10. So right, 10, yeah, 10. So 1 minus what, 10, choose 0. P to the X, P to the 0 was 0.25, this is 0.25 to 0, times 0.75 to the what, 10 minus 0 is still 10, so 10. By the way, something to the power of 0 is equal to 1, not equal to 0, okay? So don't just go put 0 and for the rest, and 1 minus 0 is still 1. So let's see, 10 choose, well, how many way there's nobody's not making a purchase? Well, there's only one way, right? Nobody making a purchase. So 10 choose 0 is 1. Let me put another space here. So here 1 minus 1 times 0.25 is still 1. 0.75 to the 10 is 0.0563. Times 1 is still 0.0563. Subtract from 1. I got, let me put my answer up here. Okay, I'm running out of space. So I got 0.9437. The probability of at least one person making a purchase is pretty large, right? Roughly 94%. Makes sense, right? At least one making a purchase. Now, at least one making a purchase is not the same as all making a purchase. Remember the first question here in this one, all 10 shopper making a purchase, and you'll be looking at it like that. I mean, it look the same thing, right? You have one from 1 to 10, but this is different argument. What I meant here in the first one is all of them making a purchase at the same time, right? So first and second and 3 and 4, that's rare, right? All 10 of them. For the second scenario, I want to know at least one. So it does not mean all 10 making a purchase. It could be, but it doesn't mean. It means that one making a purchase, and 2 making a purchase, and 3 making a purchase. There's a lot of possibilities. You add them all up, right? It's the or here. It's the or things here. So it should be large, right? 1 making a purchase, or 2, or 3, or 4, right? You add them all up. So when you add something up, you should have a bigger probability as opposed to the and part. Remember what I say? And probability, it should be smaller, have a smaller probability, but restricted. All right. Number 4, how many shopper in your random sample of 10 online shopper would you expect to actually make a purchase? I'll give you a second to do this one. Or you can pause it, right? How many shopper in your random sample of 10 online shopper would you expect to actually make a purchase? Well, I'm going to show you a formula, which you see the next slide. But before I actually show you the formula, I want to explain it to you. Expect to actually make the purchase. What you can do, well, let me use the formula. I'm just going to spill the bean here. The expect mean what? Expected. Remember, you guys see this on your exam? I remember the first exam, right? Expected, the expected value. Expected value. Oops. Forgot the ED. Expected value. Remember the notation. The notation is what? E of X, big X, equal mu, right? It's the same thing as population mean. Well, in this case, it's N times P. N times P right here, N times P. Right? So N is what? N is 10. P is 0.25. 10 times 0.25 is 2.5, right? So there are 2.5 shoppers will make the purchase. By the way, for the expected value, do not round up or round down. Leave it like that. I know it doesn't make sense. Like you cannot have 2.5 shoppers, right? But it's the rule. For expected value, you don't round. Just leave it as is. I didn't make a rule. All right. So now one way of thinking, like if you don't know the formula, how would you calculate this? Well, you can make a table. Right? You don't have to write this down. You're never going to do this. I'm just going to explain it to you how you come up with 2.5 out of the argument, right? You can make a table, right? You make a table. Here is your X. Here is your probability, right? X is what? 0 people making no purchase, none making a purchase, 1 making a purchase, 2, all the way to what? 9, 10 people making a purchase, right? And then you have a probability down here. we already know what is probability of none making a purchase. We have right here, right? Probably 1, 2, and then you add them all up. You sum them all up. That's summation, a notation, right? You sum them all up. X times P of X. 0 times, so 0 making a purchase, what 0 making a purchase is 0.0563, right? We did it up there. So 0 times 0.0563 plus 1 times, what's 1 making a purchase? I forgot. And just, well, you can calculate it out. 10 choose 1 times P to the X, 1 minus P to the N minus X, right? And then you add them all up. The final answer should be 2.5. But don't on the exam, don't do that, right? Just use a formula, N times P. N times P. All right, make sure don't forget the notation too, very important. So here is the, if X have a binomial distribution, then the mean of X is the expected value, A of X, equal mu equal N times P. And the standard deviation is sigma equal square root of sample size N times probability of success P times the probability of failure 1 minus P. You can find this in the formula sheet on Moodle. Okay, try it. Suppose that 10% of Americans are left-handed. Let X represent the number of left-handed Americans. Remember, X is the number of success, right? Here, the number of success is defined as left-handed. In a random sample of 12 Americans. So the sample size is 12. So we have N, right? Do we have two outcomes? Yes, either left-handed or right-handed, right? Each outcome is independent of one another. Yes, right. One person, if you were left-handed or right-handed, it had nothing to do with the next person, right? If the probability of success is remain the same throughout, yes, right. 10% of Americans are left-handed. Right? In the random sample of 12 people, this is your random sample, right? Probability if you pick out one of those people from 12 from the 12 sample here, from the sample of 12 here is 10%, right? So X have a binomial distribution. Remember, what is the formula for binomial distribution? Do you remember? Distribution B bin N comma P. Of course, you're gonna plug it in. What is, you don't have to write the black part in on the exam. All I need is the red part. So probability binomial distribution is what? N is 12 here, but probability of success is 0.1. That's it. That's it. Note that the mean or the expected number of left-handed Americans in such a random sample would be what? So this sentence they're asking for the expected values. Remember, expected value is what? E to the X equal mu. You're gonna write all out. Equal N times P. Well, N is 12, P is 0.1, so 1.2 American. I was left-handed. The standard deviation, here they're asking for the standard deviation is the square root of N times P times 1 minus P. Some other book, they say instead of writing 1 minus P, they denote it's Q. Okay, Q is the probability of failure. It doesn't matter, it means the same thing. So N is 12 times P is 0.1. 1 minus 0.1 is 0.9. Let's see, square root of what? 12 times 0.1 times 0.9. I got 1.04. 1.04. Makes sense, right? That's the standard deviation. What is the probability that the sample contained at most one left-handed American? At most one. At most one. Again, before you do anything, I would recommend you try to spot out, spot out some clue right here, at most one. So how would I write it at most one? P of what? X is less than or equal to 1, right? At most 1, right? On the, remember, at most 1 is what? On your stick, on the stick picture, at most 1, 0, 1, that's it, right? 0 and 1, that's it, no more. So this mean is P, I want it red, P of X equals 0 plus P of X equal 1. Well, you plug it in, right? What's P of X equals 0? That means 10 to 0, 0.25 to the 0, 10.75 to the 10, plus 10 choose 1, 0.25 to the first, no, X is 1 here, 10.75 to the 9. You plug in your calculator, what does you have? Well, 10 to 0, I think we did up here. This part right here. Let me remind you right there. So we got 0.0563. 0.0563. What about 10 choose 1? Have we done 10 choose 1? I think we did. Right, we did. That's the same one right here. 10 choose 1 right here, right? Yeah. 1.1877. Right, 10 choose 1 right here in green. 0.1877. Or you can use your calculator and do it all over again. 0.1877. Right, add them up to get 0.1877 plus 0.0563. I got 0.2440. So at most 1, at most 1 is left-handed American, is the chance is 24%. Suppose a random sample of 120 American has been taken instead of 12. So now X has the binomial distribution that N sample size is 120 now, and the probability of success is 10%, still the same. The mean or the expected left-handed American in the random sample of 120 will be mu times N times P equal N times P, right, which is equal to 120 times 10%, which is 12 Americans. The standard deviation for the number of left-handed American will be sigma equals square root of sample size, which is 120, times the probability of success is 10%, and then probability of failure is 90%, right? And then compute it out, they got roughly 3.3. So how might you try to find the probability that random sample 120 American would result in 20 or fewer left-handed American? Wow, 20 or fewer, so out of 120, so 20 or fewer. Now let me, so P of X is less than or equal to 20. We can write it out. So P of X equals 0 plus P of X equal 2, P of X equal 3, all the way P of X equal 19, P of X equal 20, right? Oops. P of X equal, should have a parenthesis there, P of X equal 20. Wow, that's a lot of probability, binomial probability to write out. So this is the exact probability of 20 or fewer people who are left-handed, right? You can calculate the exact, which is the way to go. Do this if you want the exact. Now, it's kind of yucky. How about you? Yeah, I don't want to do that, right? So there is a way. What if there is a way that we can approximate this instead of doing the exact? It'll be good enough, right? Well, so here is, so the next slide, I just wrote it out for you, what I wrote up here, same thing, right? So P of X is less than or equal to 20, you just add all of them up, and you have to calculate all of these out, and that will be your exact values. So these are exact value But I don't want to do this way, right? There is an easier way that let us approximate this. What if when we can just approximate this, it would be close enough. We don't need to know the exact value. Oh, it should be number 20 here. My bad. Should be 20 or fewer. Right. And there is a way involved using the normal distribution. Yay. Normal distribution. Remember the density curve, right? So the normal distribution can be used to approximate the probability for other types of random variables. One being binomial random variables when the sample size n is large. When n is large enough, you can use a formula. It's called normal approximation to the binomial distribution. Okay, so sample size is important. I don't know about you, but in statistics, sample size is really important. Remember back in the how we learn how to sampling method. If your sample size is large, tend to be less biased, right? Not always, it's not always true, but that's general case, right? Sample size large is likely that you have less bias, which is good, right? So here is sample size large, you can use a normal approximation to the binomial distribution. Okay. So how large is large enough? Right here. How large enough? If you take n times p, sample size times the probability of success, if it at least 10, and n times the probability of failure, 1 minus p, at least 10, then you can use a normal approximation. X is the normal, approximately normal. Okay. In this problem is, you can do that. In this problem is what? In this problem, n is 120, right? Probability of success is still 10%. So 12 times 120 times 10% is, which is 12, definitely greater than or equal to 10. So we're good, right? Over here is 120 times what? 0.9. 12 times 0.9 is 10.8. Well, is definitely greater or equal to 10. So yes, we can use the normal approximation instead of calculating all these out, right? Now, how will we come about this? How will we come about this? 20 here. All right, before I actually go to that problem, I want to show you a model, example of binomial models here. It had nothing to do with the problem, the left-handed problem we did, but we'll come back to it, okay? I just want to show you how the sample size affect the approximation models. Okay? So here is example binomial models and the normal approximation as n increase, yp equal 10%, right? So here, oh, maybe it is. Maybe it is. Yeah, maybe it is. Yeah, it is the same problem we did. Yes, it's the same problem. It is the same. So when I have n equal 5, right there, n is 5, and probably success is still the same, right? 10%. The curve look like this. All those stick when I put a density curve, draw a density curve, it looks like this, sort of a right skew. What about when I increase from 5 to 10? From 5 to 10, it looks like this. Right? It looks a bit better, a little bit better. What about when we increase to 25? Well, definitely normal, right? Definitely look like normal. What about 50? Even better, right? All those stick kind of get together and they get more and more normal. They look more and more normal. About 100, 100, 1000. Wow, it definitely is. Look like all of those stick, all the red stick get together fast enough that it can make up into a density curve, a normal curve, right? Here is just zoom it out a little bit. It's the same thing is here, but just so tiny. We zoom it out here for you. Or I zoom it out here for you. So it looks very much like a normal distribution, right? So therefore we can approximate when n is large enough, right? Okay, so return to the problem, left-handed problem. Remember the mean is still 12, right? The mean here is just, I'll just repeat what the other the previous slide, and the standard deviation is 3.2. So you can draw it out, right? Remember the normal curve. Mean is what? Mean here is 12. So n is 12. Standard deviation is 3.2863. 20 or fewer, 20 or fewer. Where is 20? Say 20 or fewer is right here. Say 20 is right here. 20 or fewer. If fewer, so you're gonna highlight the left curve, right? Because 20 or fewer. And remember how do we do this? You can use Google Sheet, right? Norm dist. Remember norm dist, or you can use the formula. What? Z equal x minus mu divided by sigma. X is 20 minus mu is 12. Right, sigma is 3.2863. Let's see, 20 minus 12 divided by 3.2863. Do it with me, okay? Don't just take my word for it. I make mistake just like everybody else. 2.43. I'll just say 2.43, and then you look it up on your table. 2.43. Look it up on your table. What do we have? Let's see. Look it up here. Sure. I think I have a table here with me and 2.43. 2.43. Maybe not. It's the same. My table a little bit different. Okay, but so it should be big. 0.9925. I got P of x is less than or equal to 20 is 0.9925. Now you want it from the left, so you don't have to subtract, right? From the left, or you only subtract if you want this part, the blue part, the greater than 20. You subtract from 1, right? Because from the left, we leave it like that. Right? So pretty a lot, right? The probability of 20 or less fewer left-handed American is roughly out of 120 is roughly 99%. Wow, it's a lot of left-handed people among us. So this is the approximation. Now, so this is the approximation of the exact value. What is the exact value? Let me remind you. Here is the exact value, the one I highlight in green. You can calculate it out. All of those from 22.0 all the way to 22.20, and you're gonna get something 0.99 something, right? It's very close. It should be close to what we have, which is approximate values. This is approximate value, but it's good enough, right? I would rather do this than doing 21 computation. But it's good enough. Okay. All right, that's be it for binomial distribution. Good luck, and I'll see you again after the break.